Okay, so last time we were seeing an algorithm for something very simple. So what was the problem? The problem that we were studying was counting number of elements in a stream. Okay, so we first observed that we can definitely give a very simple deterministic algorithm that takes order log n space. Okay, and one can easily show that this is, you cannot do better than, or basically log n bits. Okay, and we can show by pigeonhole principle that this is optimal. Okay, and then we relax this condition that fine, if I wanted to compute things exactly, then I cannot take less than log n bits if I want to count n items in a string. Okay, so then we relaxed this condition and we said fine, we are happy with, if there are n items, you can give me an n tilde which is in good range between them. Okay, so in some sense I said let's get some, here is your real n, you can give me an n tilde, you can return me an n tilde which is like n minus epsilon n, n plus epsilon n. So this is basically 1 plus epsilon approximation to the number which we have been trying to achieve. Okay, and to do this I said okay fine, so let's just first try to get a factor half approximation for our problem. Okay, and to do that we realized that we could achieve this if we could somehow do this, the trick of bucketing trick, right? Here is like 1 which is basically 2 to the power 0, this is 0, here 2 power 1 which is equal to 2, 2 power 2, 2 power 3, 2 power I plus 1, so on and so forth, right? If I know, if I could tell you that my number n, the number of items n is in this window, right? And then if I can return either of the extreme, say for example if I know that this is in some 2 power I minus 1 and 2 power I, then whatever number I return, it's a factor 2 approximation to this, right? But we didn't know how to do this, right? And then that is why we moved to a randomized way of incrementing a counter, because what will happen if we could do this? How many numbers are there, right? How many buckets are there? Just log n buckets are there. So how many bits do I need to remember per bucket is like log n bits, because by that. So from log n I could get to a log n space in terms of bits, we have like reduced exponentially at the cost of something. Okay, so that was the goal, and this is what we were trying to implement in the randomized setting. Okay, and we also implemented it. So what was our Morris? So this was an algorithm due to Morris from 70s, and the algorithm for Morris is as follows. So you have a counter x. Okay, you initialize x0. So this is your counter which you like to increment. Okay, so what did it say? For each event increment x with probability 1 over 2x. For each event increment x with probability 1 over 2 power x. Okay, and what did we do? Third, output 2 power x minus 1. This is what our algorithm was, right? So right? So if you think about it, what is happening is that in some sense, if you look at a range between say 2 power I and 2 power I plus 1, basically this is trying to pick one of these, like if you look at an equal partition, then it is just trying to find, like trying to increment each of this with like uniformly, like I did here, I did here, I did here, but with probability 1 minus 1 by 2 pi x, I'm also not incrementing, and with randomization that takes care of things. But this is basically what is happening, which I showed you how to do based on reservoir sampling. Okay, so what did we show for this? We proved that, so this is what we are outputting, right? So we showed we needed to compute, we did some probability computation, and what did we manage to show? If you recall correctly, okay, so what did we show? So this is the lemma which we showed last time. Expectation of the random variable 2 power xn is n plus 1. So this is what we showed, right? And this is why we are outputting 2 power x minus 1. So this is what, and this we showed using induction, okay? But this only tells us that I achieve this expectation, this. But what we needed to show, we need to show the following thing, okay? Probability, so suppose this is what you output, and let's say this is n tilde, okay? I need to show you n minus n tilde is more than epsilon n with probability less than delta, because my goal is that you are within the range with high probability, right? So what does this tells us? Okay, n tilde minus n doesn't matter, right? So this is what is, if my n tilde is at random variable, what is n tilde minus n? N is basically your expectation of n tilde, because expectation of 2 power xn is n plus 1, okay? So our goal was to show that we achieve this with good probability, which means that probability, what we needed to show is n tilde minus n is less than epsilon n with probability at least 1 minus delta, which same as showing that I am out of bound, like I lie here or I lie here with probability at most delta, okay? And to do this, what did we apply? We said let's apply Chebyshev's inequality. So either we can apply Markov, right? So what happens if we just apply Markov here? What will it say? Probability that n tilde is more than, what is Markov? If we have to show that probability n tilde is greater than some epsilon times expectation, is what? 1 over by epsilon. So what do we mean by epsilon? Fine? Is this not true? Forgot what is Markov.
The expectation of x by a, right? Probability of x greater than a is expectation of x by a. So the whole thing will be in the denominator. So it will be just one outside. It will be expectation of n tilde by.
Wait. What is this? So what is that probability greater than lambda is less than equal to expectation of x by lambda, right? So fine. So if I do this, what will be this? Probability that is upper bounded by 1 over epsilon. If I just applied this, this is what I will get. So what does this tells us? If I put even for half, does it make any sense at all? Even for epsilon equal to half, it makes absolutely no sense because all it says is less than 2. Right? Fine, so then return 0. I mean, sure it is within this range. Right? Okay. So this is why we needed to compute. So this tail inequality like Markov is not good enough for this case. So we need to apply a stronger form of tail inequality, and what we try to do is Chebyshев. So what does Chebyshев says? So what does Chebyshев says? It says, so the bound which we applied was that probability that x minus expectation of x is less than equal to, what was that? Right? It was expectation of x minus expectation of x whole square by lambda square, which is basically variance of x by lambda square. Okay. So notice that if I wanted to compute this quantity, what we needed to compute? 2 to the power 2xn, and this is what we showed last time, or we assumed last time. So what did we get? Expectation of 2 2xn was equal to some 3 by 2 n square. Let's see. Okay, so we got this is 3 by 2 n square plus 3 by 2 n plus 1, right? This is what it is. Okay, so given that we know this, given that this, we can compute this, right? Because what is expectation of n tilde minus n whole square, because this is what our random variable is, this is what we are supposed to compute, x minus expectation of x, and we did this computation, and what did we get? If you recall correctly, this was like variance of 2 power xn minus 1, which was equal to, we got half n square minus half n, which is less than equal to half n square. This is what we got last time. Okay, but even this, now even if I go and substitute this, what are we going to achieve this? So now we are going to get probability that n tilde minus n is greater than epsilon n is less than equal to 1 over epsilon square n square by 2, which is n square gets cancelled, right? So even this was not good enough for us, because even, look, if I wanted epsilon equal to half, right? Epsilon equal to half, what does this tells us? Right? So probability that this is more, like we will get the probability that this is greater than n by 2 is less than equal to what will be here? Half or 2. Does it make any sense at all? Okay, so and if I substitute epsilon equal to 1, then I get half. So if I substitute epsilon equal to 1, so if I want the deviation from n tilde, what I output from the number of items to be n, only then this probability makes sense, then I can just better output 0 and I'm still within the expectation, right? So what did we learn from this? So we learned from this that these two things are not going to work. Okay, so then we applied this trick of Morris plus, and let me tell you what does variance do? So what does variance do? Right? If you look at this quantity x minus expectation of x, basically it measures the difference between your some random numbers, and it's how much these random numbers deviate from its mean and the square of it. Okay, so now when you take not one instantiation of these things, but if you take say t instantiation of these things and then take averages, what happens that these local gaps over an average cancel out each other and one extra factor just comes out. Okay, and that's a basic idea why we will see that in such kind of algorithms we always we always apply like this trick of running it t times, right? Because if you look at, I mean, if you do just simple maths also, what is a variance of a times x, where a is a constant, is nothing but 1 over a square times variance of x. Like, okay? And that is a very helpful thing to have. Okay? So now what we did last time is we did Moore's plus. And what is Moore's plus algorithm? Well, Moore's plus was very simple. What we did S independent instantiation of Morris. Okay, so say let's call this algorithm MS. Okay, so we had MS1, MS2, MS. Okay, then I got estimate from each of these guys, right? So I got N1 tilde, N2 tilde, NS tilde, but what do I return as my algorithm? I just take the mean average of these things and I return N tilde as 1 by S over Ni tilde I going from 1 to S. Okay? What will be expectation of N tilde? It's going to be the same thing, because by linearity of expectation I'm just going to count this average, S times that and divide by that, right? So expectation of this new method is also is going to be what? Is going to be N, right? Because look at Ni tilde. What is Ni tilde? It is 2 times some Xi tilde, so that will be like some minus 1. So N how many times? S times. So Sn divided by S is again this. Okay, so this is fine. We are still with respect to the expectation. But now, what did the variance computation tell us? Exactly. So variance will be probability that N tilde minus N is more than epsilon N is now, for this, is going to be 1 over 2S times epsilon square. Okay? Okay, excellent. Now, but what was our goal? Epsilon was given to you, delta was given to you. You wanted that the deviation from expectation is, or you are giving me 1 plus epsilon approximation, right, with good probability. So your accuracy is high. So I would like this to be less than equal to delta, right? This is my goals. I would like this quantity to be less than equal to. So how many times do I need to run this algorithm? This tells us that, well, if you want delta accuracy, then S should be less than equal to 1 by 2 epsilon square times delta. Okay. Okay. Now there are several questions people asked me last time, which I will not prove to you, is that why the space here? So now for one particular instantiation of MS1, this N tilde is going to be N plus 1 with very high probability, right? It means the space which I am going to take for each of them is like log in space, right? Now you do enough, like you gain enough so that you can show by union bound that over all of this also you are achieving this with high probability. So the amount of space you are going to take in each instantiation is log n. But that requires proof. I will put that in an exercise. Okay. Okay. So what did we achieve from here? Okay. So now there is a very simple trick. So now notice that we have to run this algorithm how many times? Like 1 over delta times. I would like to remove the dependence of delta and achieve the same thing, right? Because then that will reduce us the number of times we have to run this algorithm, right? We would like to improve the, what do you call, a space bound. So currently what will this gives us a space bound? If you look at this, epsilon square delta log in space. Okay, I want to like I do not know what to do with epsilon square, but I would like to reduce the dependence on delta. Okay, so let's see how to do this. So the way to view this is that, okay, fine, I'm achieving this, like this is like I achieve this with constant probability. So it's like a constant probability success at this round, and then I boost this constant probability of success by bunching things and then applying Chernoff. Okay, so what I mean by this is that let's succeed slowly, slightly here, okay, and then we will succeed much better at end. So what I mean by this, so suppose, so this is a trick which we will keep using several times, so it's better to learn. Okay, so now I made Morris plus. Now let me make this algorithm called Morris plus plus. Okay, so if I wanted to succeed this with, say, delta equal to 1/3, fixed constant 1/3, then how much space each of these guys is going to take? Log n by epsilon square, right? Then each instantiation is going to take log n epsilon square, right? Okay, fine. Okay, so now what I do is the following. Okay, I run. These algorithms are called MS plus. Okay, so what is Morris plus plus does? It calls MS plus t times. Okay, and then it is going to return again the median. Okay, so again I got some. So from MS plus, I would have done something. I would have got n1 plus, n2 tilde, nt tilde, and what I'm going to return? I'm again going to return 1 by t times ni tilde, I going from 1 to t. So now think of this way, like I had a very basic algorithm who achieved something. Then I just ran things in parallel and I was able to show you that I can achieve certain things. Now I group them, right? It's like, what are you returning n1? It's like median of medians. And what I'm outputting? Again, median of medians. Okay. Now you ask yourself, now but I'm not applying this MS plus 1 just like this. These are applied with delta equal to 1/3. Say delta prime equal to 1/3, because delta is what I want to achieve, right? So now you ask yourself, what is an expected, so look at this guy. I say that this MS plus has failed if, like, it should have returned me within epsilon bound, but it did not return me in epsilon bound. So what is the expected number of times will I succeed? Okay, so let me make it more formal. Okay, so I'm going to write yi is 1 if MS plus I succeeds, 0 otherwise. And what I mean by succeed is that means that you have returned me a number which is between these things. Okay, so my question is, how many times, what is an expectation of y, which is summation of yi? What is your probability that you are failing? 1/3. So what is the probability that you are succeeding? Is 2/3, right? So yi is a random variable. What is the probability that yi is equal to 1? 2/3. Because they are I should say at least 2/3 because they are failing with probably at most 1/3, right? That this is what I applied my algorithm with, right? That look, you are applying with delta prime equal to 1/3. It means the error is bounded by at most 1/3, right? So with probability 1/3, 2/3, I succeed. Okay, so then what is an expectation of y? Okay, but you tell me, why will this algorithm fail? Because this algorithm can fail only more than half the time your estimators like these MS ones have returned you wrong answer. If more than half the time your median is correct, you are never going to return wrong answer. Right? So to return wrong answer, it has to be true that at least half of them have given me wrong. So what is that means? That probability, what is the probability that the random variable y, right, is less than t/2? Okay. So what is an expectation of this? 2/3. So if I have to write it in a way, then what it will be? If I write down, is this correct? I just rewrote this. You take this here, you will get t/2, right? But what is this? This is an expectation, right? So this is probability y minus expectation of y less than t/6. I can apply Chernoff now, right? Because these yi's are independent because I am just running it in parallel. They are not related to each other. And what did Chernoff told us? Is like this is upper bounded by 2 times e minus, what was that? Does anybody remembers Chernoff?
Should it not be different? It is y less than t/2, right?
Yes.
So y minus 2/3 should be greater than minus t/6. Sorry, less than minus t/6.
So put mod. Is that fine? Is this fine? Okay, you're right. Okay, put mod because it could be either way. Okay, so what was the, okay, it is t time, so what was Chernoff? Chernoff said that probability that x minus expectation of x, right, is greater than equal to epsilon times mu, where mu is expectation, right, of the this is like 2 times e minus epsilon square mu by 3. Okay. So what will be in our setting? So it is 2 times e minus epsilon square, right? So what is our epsilon square here? What is our epsilon here? So it should be something like 1/4, right? So it is t by 1/12, right? Is that okay? Yeah, something of this nature, right? Huh? And all you have to show that this is less than delta. All we need to show this is less than delta by choosing t appropriately, right? But it's like what it will be? It is going to be some log 1 over delta. If we do this computation, what is going to get? Log 1 over delta, right? Let's see. So this is what we have to show, right? 2 divided by E t by 12 is less than or equal to delta, right? So E t by 12 should be less than or equal to 2 over delta. So if I take ln both sides, what I'm going to get? T over 12 is less than or equal to ln 2 by delta, right? So T is going to be less than or equal to 12 times ln 2 over delta, which is order 1 over delta, ln 1 over delta. So now I have improved my dependency from delta to ln 1 over delta, right? So now we are taking much less space than before, right? Because now we will only multiply with this how much times? So we have to run this algorithm ln 1 over delta times. So you replace 1 over delta with ln 1 over delta. Right? Yeah. Because we applied for 1/3, so delta is not going to come there. And then you have run this much time, so you have saved this space. So this is what is called Morris plus plus, okay? And so what is the best known bound, which I'll put it in the exercise, is that the best known bound is actually you can achieve okay, so let me write it down, what is best known. And that's also lower bound is order order log 1 over epsilon log n. This is what the best known is, and we can achieve this. So how do we achieve this is not very hard. It's like you don't fix 2 here, you fix some a power x, like you fix not 2 power x, but you do it with some a power x, and you fine tune a appropriately to get the best known, okay? Okay, so this is our first algorithm, okay? And but the upper bound was known from long time, but the lower bound was only proved much later. So what I'm going to do now is going to teach you what I call counting distinct elements in a string, okay? Okay. So look, our problem was very simple. All we needed was count number of items, right? But I mean, if we allow randomization, let allow approximation, then we can achieve like exponentially better space bound and get close to the number which we wanted. Okay. So now let me go from here, and we will see all the 3 steps again for this algorithm. We'll make a basic form, not going to work, repeat bunch of times, it will work, but it will give us some way constant factor approximation. Okay, fine. And then finally, we bunch this constant factor approximation, right? Because you are succeeding more than half, like because there was nothing in 1/3, we could have chosen 1/4 also, then we would have won 3/4 times, and like, so you just go beyond half for victory in terms of number of places, and then you can apply Chernoff, right? So this is a basic step. So what is this? First, variance is low, I repeat several times, variance decreases, I achieve constant factor approximation, and then I boost this constant factor approximation by running the median trick, or the majority. This is also called majority trick, okay? So I'll show you once, and after that I will never show you in the course. Okay, so now what is the problem we have? So I want to count distinct elements in a string, okay? Counting distinct elements in a string. Okay? So elements are coming, and so where are these elements? So the setting is there are going to be I1, I2, Im elements coming from 1 to n. Okay? So this is your guarantee that these numbers are going to only come from this range 1 to n, and you want to count, what is an objective? To count number of distinct elements. Objective to count uh, number of distinct elements in small space. Give me any algorithm, like any trivial algorithm. Okay, so he wants, so your solution is, his solution is keep elements, and when a new element comes, check if it is there. If yes, discard. Am I right? Else keep. Okay. How much space will this take? Which could be in worst case. So how much space will it take? In terms of bits, how much space it will take? Huh? N log n or m log n, because there are m things coming. Is there any other solution? Because there are m items coming. No, these numbers are from the range 1 to n, and only m of them are coming. M could be, for now, just assume that m could be much smaller. Yeah, so it could be as bad as all of them are distinct elements.
There are only n that can be distinct because they're coming from 1 to n.
Truth.
Or m could be less
Than n, yes. But what else could have been done? But so it is right when m is, this is a very good solution. But suppose m is of roughly the same order than n, then can we come up with something better? Like, because then this will be a very bad algorithm. Like for example, m is like n by 2, then it is like n log n bits we are keeping. Okay, so another could be, as he says, is that you keep n bit string, right? And you increment the number which you see, like you increment the bit. So all are 0 in the beginning, okay? Increment the bit to 1 if we see that element. right? And you just increment once because we are only interested in distinct number of elements. So number of bits that we will store is n. So it appears that we can achieve minimum of m log n bits. But how will we achieve simultaneous, like if you knew m, then you could do this. You get my point, right? Whether to go to this strategy or whether to go to this strategy, if I did not know m, how will I decide about it? That's the first question, which I will not answer you this lecture, but this is something to think about it. This can be done deterministically, that we could achieve this, okay? Good. Now, suppose, so you got the problem, you got the two simple solution, okay? Now, we are going to be in the regime where I'm happy if you are going to give me some estimate on number of distinct elements, okay? So suppose if I allow you, say fine, given, suppose there are t distinct elements, okay, t distinct elements, and if I ask you, can you give me a t tilde such that it is deterministic algorithm, and secondly, t tilde is 1 minus epsilon times t less than equal to 1 plus epsilon times t, where t is an actual distinct elements. So I'm not allowing you randomization. All I'm allowing you is that you can give me an approximation to the number, right? But you have to give me a deterministic approximation to this number. It turns out for that also this is a lower bound, and we'll prove this, okay? So okay, or I ask you to give me exact t with probability at least 1 minus delta. No approximation, I want exact t, but with very good probability, okay? Again, star is a lower bound, right? So if I allow you just approximation and seek deterministic algorithm, you cannot do better than whatever we just did. I allow you randomization but do not allow you approximation, that still holds as a lower bound, and we will see at least one of these lower bounds in the next lecture. But suppose now I allow you both, right? I give you a power of approximation plus randomization, right? We can actually achieve polylog in space. Okay, so what I mean by approximation, the way we were doing last time, right? I will give you a t tilde. So what will this probability that t minus t tilde, doesn't matter if you write mod, is greater than epsilon times t is less than delta, right? So this is what we can achieve in, like, of course there will be some epsilon delta based on this error space. In fact, we can achieve much better than that, but better than this, but at least in this class, this is what I will teach you. Okay, so first let's go about it and see what we are going to, how we are going to achieve this. So first let me tell you what I call idealized solution. Okay, I will tell you in a minute why I call idealized solution, because you will see that this is not easy to implement or easy to achieve, but So suppose you knew in this problem your n. Then can you do these two things simultaneously? It's a good question to think. Okay, so the solution which I am going to present to you is by this person called FLA Flazola and Martin. Fox 83. Okay. 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 So let me just write down this algorithm. Okay. And I'm quite sure you will not understand why this algorithm actually works, even after I write down this algorithm. Okay. So let me write down. Okay. So I will call it idealized algorithm. Pick a random function h from 1 to n to open interval 0, 1. Okay. This is why this algorithm is idealized. How will you store this h? Right? I mean, how will you store this function? It's like random function over real numbers and everything, like, I mean, some precision. So forget about logs, polylog in space. I mean, you might just end up. But for now, it's good for intuition. Okay? I'm going to, okay, so suppose I had this, okay, random function from 1 to n to 0. What should you think should we be storing and outputting? Okay, so let me ask you, fraction of
Fraction of times, number of times the element appears by total number of.
no, you should have some intuition. So suppose this is a 0, 1 and n is 1. What do you expect a random function to be? Where it should be? Roughly 2. What, where will this be? These 2 points will be with very high probability. Think of this as a closed unit. Okay, if I give you, so what does it mean? Suppose if I had 4, where it will be? Okay, suppose I had 4, so wherever it is, I go somewhere else, I go somewhere else, so that these are roughly uniform. So what does it tell us? Look, this is a function, so whatever the numbers is going to come, all the same element is going to be just mapped to the same number. So that's perfectly fine. Just suppose idealistically, I had two elements, and then where will I be mapping my first element? At 1/3. That tells me number of elements roughly. If I knew what is the fraction I have and that is uniform, then I know where the number is. So what I'm going to store is maintain a counter x, okay? And what is it going to store? It is going to store our minimum I in stream hi. That's it. This is what I'm going to store. Then what I'm going to output? -1. If our intuition that this is going to like do this correctly, then I stored whatever the number, smallest number, like whatever the smallest index the guy has gone to, that is 1 over x minus 1, and that tells me the number of elements which we have. If I had 3 number, you have put 1 at 1/3, 2/3 this, so if I take its reverse, then 3 minus 1, that gives me the number. Right? If I had a 4 number, you were going to make it 1/4, blah, 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 right? Then that minus 1 gives me the number. I mean, of course, we need to do analysis and everything, right? But that's an intuition, right? That a random function has all these good properties. So it's a random variable which is minimum of t independent uniform 0, 1 random variable.
The numbers of elements that you were saying, that is n or m?
M.
Why? Because your h function is fixed, right? It is
I know the total, I know universe.
yes. So h is from n to 0, 1.
It's a closed interval. It's a closed interval 0, 1, yes.
So now, whatever be the number of elements that you'll be getting in this tree, h, the assignment that h is doing to the elements, to the numbers 1 to n, are same, right? So how are you giving an estimate of m by doing 1 by h minus 1? We want to estimate m, right?
Yes.
So h is a fixed function irrespective of whatever m is.
Pick a random function. So when my algorithm is going to come, I have picked up a random function from 1 to n to 0, 1. Correct?
So irrespective of whatever n is, h assigns things to every element of 1 to n, right?
Yes, it does.
So then if I want to say that it will be like, if we assume that it will be like distributed uniformly
With respect to,
with respect to what? Not all the elements of the universe.
but it is uniformly with respect to every subset of that. Think about it. Let's compute his expectation and see what happens.
With the intuition you gave, you considered m to be this, right? 3 or 2, whatever.
Yes.
And then
That's a good question. Okay, I'll tell you why it is. How can I think of this h? When a number comes, right? How can I think of this? So what is my x is? X is minimum of t independent uniform over 0, 1 random variables. This is what it is. X. So all burden on me is to show that if there are t distinct elements, then my expectation is something, 1 over t plus 1. That's all my burden is. And then I'm good. If I can show to you that my expectation of this is 1 over t plus 1, then I'm good. And this is a continuous random variable. So what is an expectation? 0 to infinity, probability x is greater than lambda d lambda, right? So let's just do that. Which is same as probability for all I in stream d lambda. Why? Because I told you, right, this is a minimum of, like, so what is the probability that x is greater than lambda? And x is going to store minimum of all this. So probability for all I in stream, hi has to be greater than equal to lambda. Okay. Now, what are these things? These are independent random variable. So I can just write down product, right? Product going from 0 to infinity, say some r equal to 1 to t, probability HIR is greater than equal to lambda times d lambda. Okay? And what is the probability that HIR is greater than lambda? Is 1 minus lambda. Okay? Okay? Okay, so what will this be? Now you can do some substitution and blah blah blah. So can we do some substitution here? If I substitute u equal to 1 minus lambda, then what will I get? No, this should not be lambda, it should be t. Right? What will we get? U power t, right? And this will become 0 to 1 du. There should be some minus 1 as well, no? No? If I would have written 1 to 0, then yes, but I wrote 0 to 1, so this is taken care. At least this much integration was fine in the morning, but maybe this is, but isn't this 1 over t plus 1? So there are several ways of looking at it, okay. I picked a random hash function for 2 reasons. Look, I like for every element I only wanted to map to certain place, right. Now, and I'm independently assigning these things to these. So think of this as like it's like so suppose I make everything into 1 by n piece, okay, 1 by n piece each. Now I want to divide this equally into 4 pieces. What will I get? Take first. So you have done unit division, and now you are summing them up. So what number are you going to get? Tell me. One. Suppose I had half, and I had 1 by n, 1 by n, 1 by n. So what is this number here? It will going to be half. That's perfectly fine, no? Now you see why this algorithm works? This, yes? Just think, no? If I had 2 elements, so 1 by n, 1 by n, n by 3, right? So 1/3, 2n by 3, like 1 by n, 2 n by 3 into 1 by n, and n will get cancelled. That's the point, right? So I have gone into small. So of course, this is exactly what I said. For any subset, if I take and just view them as like just on them, it is still a random function, which is equally placed. And this is exactly what this shows. Right? So like I have gone into unit, like basic unit, and then on top of that I'm taking uniform. So right, so yeah, I will be here, you just sum them up. So this is why even if I fix one function, I'm still fine with it. Okay. So we are done with expectation of x. Okay. Now we have to do, so we did all this 1 by t plus 1. What is, so let's try to again apply Markov. What does Markov says? What will, look, I want to achieve this with good probability, right? So what will Marco tell me? Probability that this is my random variable, right? So now it is correct, right, that we are outputting t, right? So forget about, so what is the probability that, say, let's talk about x itself, forget about 1 over x. What is the probability that x is more than 1 over t plus 1 times epsilon? Is again going to be less than equal to 1 over epsilon, as you said before? Useless bound. Right? So we need to do something, right? Okay, so for now let's just compute expectation of x squared, just keep it like just, it's not some fun, but it's okay. Okay, okay. So what I'm interested in, because I want to apply, now I want to apply Chebyshev and see what happens here, right? So I would like to compute, so Markov was very useless for us, it didn't give us anything at all, it says, okay. So now I'm interested in computing, I want to apply better tail bound inequality. So I want to compute Chebyshev's, then I need to compute expectation of x square. So expectation of x square is what? It is a same thing d lambda, right, which is same as saying root lambda d lambda, okay. Please do the computation, I will tell you what the number comes, because I mean this is not something, it will come 2 to the 2 t plus 1 times t plus 2. Okay. You can just do the similar kind of substitution, but this is the number you will get. I mean that's not important how you get, but this is what you will get it, and this is a method to show. Okay. Then it's an usual computation. Okay. Then what is variance of x? Expectation of x square minus expectation of x whole square, and we have both, right? So this is like 2 by t plus 1 times t plus 2 minus 1 over t plus 1 whole square, right? And now this looks like this is less than equal to 1 by t plus 1 whole square, which is expectation of x whole square. So this also will not give us much, even if we applied Chebyshev. So what did we do to reduce the variance last time? We ran this algorithm for certain number of instantiation. So let's apply that trick and let's see what happens. Okay. So we will going to call it, because of the Fazule, and so we'll call this basic algorithm FM algorithm. FM. This is what is, so if you look at all this literature, now I understand what is FM means. I used to think that there are something, but no, it is because of the name. And then you will learn AMS, which is Elon blah blah. Okay? Okay. No magic. So we have done all the hard work. Now we are just going through the motion once more to but look, this algorithm just keeps one number, right? If we forget about what we do with h, right? This only maintains one number, so that's like log n bits, right? So in this idealized situation, we can achieve log n bits, right? But we have to somehow get rid of this h in a nice way. Okay, so let's do first Fm plus. Okay, so what is Fm plus going to do? It is going to instantiate independent iterations of this. Okay, so instantiate Q, let me write down how many of them. Eta FMs independently. Okay, so we have FM1, FMQ, and they are going to give me some numbers. Okay, they are giving me some x1, xq. What should I return? Look, I was returning 1 by x minus 1, right? So you have to output 1 by z minus 1, where what is z? Is a mean of these guys. So it's not always the mean of the but you have to look at which random variable, what gave you, and do this. So we are going to return 1 by k q of xi. Tell me, what is your expectation of z? Will it change? Will it change expectation? By linearity of expectation, this into this divided by the same number, so expectation of z is still 1 over t plus 1. But what is variance of z? It is 1 over q times, so let me write down, okay, maybe this will be useful for you, okay. So just this is note, I mean this is something which you can prove, this is like proved in everywhere. So variance of a times x, where x is a random variable, is 1 over a square variance of x. Remember, this is like a square. A times x. Sorry, yeah, it is a square into variance of x. Okay, you're right. Okay, my mistake. It doesn't matter. So now if I apply this, we know I want to compute variance of z here. So what is variance of z here? It's going to be q square time okay. So it is going to be 1 over q square, because we have z is 1 over q, right? So I have multiplied them, times, why are we getting t? Plus 1 square. What was variance of z? What was variance of z? No, there's something. This is for 1, right? This is for 1. So what this is going to be? Q times whatever this is, because look, for each variance of z, I mean, look, these xi's are independent random variables. So I should also write down variance of z. If xi's are independent, right, then their covariance is 0. So then you can write down summation variance of xi's. Okay, only if covariance of xi xj is equal to 0 for I not equal to 0, which is true when xi's are independent random variable. Okay, so then only you can write variance of z, because so what is variance of z here? So variance of z for us is going to be variance of summation I going from 1 to q, 1 over q times xi. This is what, because of this we can write it. Now for each of them, as I told you, right, a square times this. So now what is this going to be? q times 1 over q square, and what was variance of xi? It is same as this, we have already computed there. So we will get 2 times shouldn't we get this? Whatever it is, like 2 times t plus 1 whole square, this much, by applying this bond. Okay, so then this q and this q will get cancelled, and what we will get is 2 times q into t plus 1 whole square. Okay, but now we have to, so this is what we computed. Okay. What is the probability that z minus 1 minus t plus 1 is greater than or equal to epsilon times t plus 1? I want to show that this is less than eta. This is what I would like to show. Okay, and how will we show this? How will we show this? We'll just apply Chebyshov on this. So if I apply Chebyshov on this, what will we get? So probability z minus 1 over t plus 1 is less than or equal to t plus 1 by epsilon whole square, because opposite of this, times variance of x, right? So variance of x we have already computed here, 2 times q times t plus 1 whole square. So this and this will cancel, and what will you get? 2 times epsilon square times q, right? Okay, what was q? We fixed q somewhere something. Q was 1 over epsilon square eta. So this will give us eta, right? Okay, but it is that this z is of this, but we would like to have 1 by x minus 1 is close to our approximation, right? We want this to be close to its approximation with good probability. Not only this, but this will give us a way to prove this. So this was a claim 1 which we proved here. Okay, now let's try to do this is what we are interested in, that 1 by z minus 1 minus t is, remember this is what we want to say, right? So this will be like some epsilon prime, and we can fix all this epsilon prime accordingly, okay, is less than eta, okay? So by previous claim, what do we know? By this claim, what do we know? By this claim, what do we know? That with probability at least 1 minus eta, what is true? 1 by 1 plus minus epsilon times 1 over t plus 1, right, minus 1 is equal to something. This is what we know from here. We showed that this is greater, like this quantity is more than this with less than eta. So this is with at least 1 minus eta, this is what happens with 1 by t. And 1 by 1 plus epsilon is like, you can show this is 1 plus minus some epsilon prime times t plus 1. I'm not going to show, but if epsilon is too small, 1 by 1 plus minus epsilon is same as some 1 plus minus epsilon prime for sufficiently small epsilon prime. okay, minus 1. So now you are good, right? What will you get? 1 plus minus epsilon prime t plus minus big O of epsilon prime. That's it, right? Now t, right? So this is what I wanted to show, right? So with probability at least this, if I can show this, whatever the t prime, this is the t prime which you wanted to, belongs to this quantity, right? Is within this range, then this happens with this probability. That's it. So like some simple computation will show this to you. Okay. So point was that once you are able to show that some random variable on which the whole function is dependent is within some, like is happens with good probability, then you can show that the random variable on which it just depends also happens with very good probability with just doing some computation. Okay. Okay. So this was your Fm plus. Okay. How will you go about doing? But here also, if you notice, like, what is the space? What is the space requirement here? It depends on this, right? So it is going to be, space requirement is going to be order q times log n. I'm still ignoring that how we'll pick a random function. Okay, we'll get to that in the next lecture. But what is q? Is 1 over epsilon square eta log n. And this eta is supposed to play a role of delta for us, because I did all this with eta for a reason, but we actually wanted that you gave me epsilon and delta. I want to give you this t prime with accuracy, like with confidence at least delta and accuracy epsilon. Now I can do that. I just substitute on the place of eta, I substitute delta. But again, this depends on 1 over delta. Can we make it log 1 over delta? Yes, we can make it log 1 over delta by doing our next trick again. That now we will not, so we will call this algorithm Fm plus, and then you make Fm plus plus, and with, again I will run this with success probability 1/3. So I will fix eta equal to 1/3. So this part of my algorithm is going to be, what is that called? This part of my algorithm is going to succeed with constant probability. So it's like my constant factor approximation. Okay. So what will be my Fm plus plus? What is Fm plus plus? Is very simple. Okay. Instantiate S independent copies of Fm plus. Okay, this algorithm, right? So like we first made single algorithm, then we took this parallel algorithm, like in parallel we ran, and then now we bunch them. Okay, you ran in parallel, give me an answer. You people run in parallel, give me an answer. You people run in parallel, give me an answer, and I will take that answer and return an answer. Okay, so, and we have fixed eta equal to 1/3. Now what I'm going to output? So output is going to be, suppose S copies, so Fm plus 1, Fm plus S, this returned Z1, this returned Zs. So what will I return? Again I will return 1 over Z minus 1, where G will be some of these things. Okay? Okay, so output the median of 1 by Gj minus 1, J going from 1 to S. It's like you took these numbers, right? You sum them up, you divide it by S. That's it. Okay? And what do we want to show now? I would like to show probability that T minus T tilde is greater than or equal to epsilon T with probability less than delta. That is our goal always, right? That I always wanted to output a T tilde such that it is within 1 plus epsilon accuracy, right? And we have confidence delta, at least confidence is at least 1 minus delta when we output this. Okay, so this is exactly like PAC model. Okay. And this is no difference than previous. So what I will write? I will make a random variable yi. One, if 1 over zj minus right. So if in the ith instantiation we are failing, then I put 1, 0 otherwise. What is expectation of yj? Is same as probability that yj equal to 1, which is less than or equal to 1/3. Right? You are 1 if you fail, right? This is a condition of failing, right? That whatever quantity number I have outputted you is not within the range, right? Then I give you 1. So probability that this random variable is this, So okay, so what are probability we are trying to find? What is a probability that median fails? Right? This is exactly what we were trying to bound before, and this is exactly what we want to bound now. What is the probability that median fails? And it means if what is the probability that median fails, which is same as saying summation I equal to 1 to S yi is greater than or equal to S over 2. This is the time when median will fail. If this quantity is more than S by 2, then the median will fail, because this is what failing means. Okay, then okay. So let's write down probability summation yi is greater than or equal to S over t is equal to probability summation yj minus S over 3 is greater than or equal to S over 6. And now notice this time I don't need absolute, because the absolute is already there. Okay. But now look, for simplicity, let's assume that expectation of yj is exactly equal to 1/3, because if it is less than 1/3, actually you do better. Okay, so let's just make this idealistic assumption. Assume that expectation of yj is 1/3. Okay, otherwise things are better. I can explain to you later, but for now, let's just for the computation sake, let's assume that each expectation is equal to 1/3. Then what are we getting? Then we are getting probability summation yj minus what is S by 3? It is expectation of these things, right? It is expectation of summation yj, right? Because, right? And what is S by 3? S by 6 is like at least greater than half of expectation of summation of yj. And now if you apply Chernoff here, because now I do not even have slash, so you can actually get rid of 2, and what you will get is like less than e times minus half square s over 3 by 3 should be less than equal to delta. This is what I want. So all you need to do is instantiation, find s independent copies. So if you do s like 36 or something, s like 36 ln 2 over delta, you're good. Right? So now we have reduced the dependence on eta to big O of log over 1 delta, right? Okay. So the total space is going to be, space of this algorithm is going to be fm plus plus is order log 1 over delta times epsilon square times log n. Okay, but as I said, this is an idealized situation. In the next lecture, I will tell you how can we get rid of this, but that will cost us another factor of log n here. So we'll get log square n. Okay, so we will see how we can simulate this with small space random variables, right? Like kyj independent random variables and things like that. Okay, question. Okay. So these are like very simple problems, but so something to remember is like if you make certain copies, if you run certain copies of this, you can reduce variance. That is something to remember. Okay, so that's, I mean, this computation is not important, but this is what is important, that if we have a basic core algorithm and if you want to reduce its variance, let's just run it parallelly several number of times. So that will run. So that's something to remember. Thirdly, if you want to decrease the dependence of, you might ask, right, rather than doing copies of this, why don't I just directly do like that? Why don't I run these many copies in the first round itself rather than doing this? Well, sometimes it works, but many times it doesn't work, because what happens is that once you have boosted the probability of each of this locally, then somehow the median approach seems to work very differently, because you actually go from certain kind of random variables to certain other kind of random variable. So in certain applications, you could have directly run these many copies in the first round itself and we could have gotten that much bound. But in many cases, it doesn't work. So this is why people bunch them together. It's like I reduce the error first and then I run it in parallel, right? So this is a two-step process, okay? And like at least in this semester, this is something which will, like, from now onwards, I will assume that, okay, given this, you all have to do is median, you will apply Chernoff and get whatever. So like this, I will not do it anymore in the course. Like I will give you the first, I'll compute this, and then rest 2 steps will be like, okay, you do this, you make plus, you make double plus. Other way is like, as you will notice that in many cases, Fm plus is like, okay, I want to get a 1 plus epsilon approximation, I'm first getting a constant factor approximation, and from there I'm boosting it to getting a 1 plus epsilon approximation. So if someone would have given me already a constant factor approximation, then probably I can avoid this step and run on that and achieve whatever I wanted to do. So these are the small things that we need to remember from this. That's it. Okay.